All right, buckle up, everybody. We're going on a deep dive today. And guess what? We're diving into the sun. Well, not literally, obviously, but we are diving deep into some really cool research about these things called arch filament systems, AFSs for short. They're like these giant magnetic bridges on the sun. And the paper we're looking at today, well, it's giving us some incredible new insights into how they work.
Yeah, it's pretty amazing stuff. This paper, it's using data from the Solar Orbiter mission. You know that one, right? And it's really the closest we've ever been able to get to the sun ever. It's like having a front row seat to, well, the most amazing physics show in the solar system, I guess you could say.
Okay, so AFSs, arch filament systems. Let's try to break this down a bit. What exactly are we talking about here? I'm picturing like I don't know, the St. Louis Arch, but like made of magnetic energy. I don't know if that makes sense.
You know what? That's not a bad way to think about it, actually.
Mm.
These AFSs, they're formed by magnetic fields. The
Hmm.
fields emerge, from the sun's interior, and then they connect. They connect regions that have opposite magnetic polarity. So, yeah, it's like the sun is constantly making these giant magnetic loops.
Okay. Okay, I think I'm starting to get it. So these loops, these magnetic loops, they're not like just sitting there, are they?
Oh no, no, not at all. They're constantly in motion. They're always shifting around, interacting, and that's where things start to get really interesting.
Oh, how so?
So within these AFSs, right, scientists, they've been observing these really tiny, how do I describe them? Elongated brightenings, and they call them bidirectional propagating
Oh,
brightening.
directional propagating brightenings.
Yeah, bit of a mouthful, I know, but they look like streams, basically, like streams of bright material, and they're flowing in two directions, opposite directions.
Okay, hold on. Two directions at the same time on the sun. What could even cause that kind of movement?
That's a great question. And, well, one of the leading theories is that these brightenings, they're the result of something called magnetic reconnection.
Yeah.
Basically, it's where magnetic field lines, they break and then they reconnect. And when they do that, well, it releases a ton of energy.
Ah, magnetic reconnection. Isn't that like what causes solar flares?
Bingo.
Ugh.
And the speed of these brightenings, well, it really supports that idea. I mean, we're talking speeds up to 150 kilometers per second.
Yeah.
That's a lot of energy.
Okay, wow. So we've got these tiny brightenings zipping around in these arch filament systems, probably powered by magnetic reconnection. Now, this paper it goes into a specific observation, right, of one of these brightenings.
Yeah, yeah, that's right. They looked at an event that was observed on March 4th, 2022, and to analyze the brightening, the movement, they use something called an artificial slit technique.
An artificial slit. Okay, I'm intrigued. How does that even work?
Well, basically, it's like taking a slice through the sun, if you can imagine that. They're focusing on just a narrow section of the brightening and then tracking how it changes over time.
So it's like creating a 2D view of something that's happening in 3D.
Exactly. And the cool thing is they didn't stop there. They combined that technique with data from a bunch of different instruments. Like they use the EUI and PHI instruments on Solar Orbiter.
I'm starting to see why they call this a deep dive.
Right. And to top it all off, they also had observations from NASA's Solar Dynamics Observatory. That one helped them figure out the temperature of the plasma.
Hmm.
So yeah, they really went all out on this one.
Okay, so they used all the tools in the toolbox to try to understand this thing. So what did they find? Was it magnetic reconnection?
Well, that's where things take a bit of an unexpected turn. You see, with all that energy being released from magnetic reconnection, right, you'd expect that plasma in these brightenings to be, well, really hot, like millions of degrees,
Yeah.
like you see in solar flares.
Yeah, that makes sense. So what did they find?
They found something that honestly has scientists scratching their heads a bit. The plasma. In this particular brightening, it was, well, it was surprisingly cool. Well below 1,000,000 degrees Kelvin.
Wait, hold on. Cooler than expected, but how does that work if magnetic reconnection is happening?
Right. That's exactly why this finding is so significant. Because it might mean that, well, maybe our understanding of magnetic reconnection, at least in these specific conditions, in AFSs, well, maybe it's incomplete.
So is this like one of those moments where science throws us a curveball?
It is. And it's moments like these that lead to even more fascinating questions.
Okay, I'm hooked. Tell me more. What are some of the possible explanations for this cool plasma?
Well, one thought is maybe the magnetic reconnection, it's happening on a much smaller scale than we thought.
Yeah, right.
Like what we're actually seeing is just the cooler aftermath of a much more energetic event.
Okay, so like we're seeing the smoke, but not the actual fire.
Yeah, that's a great way to put it. Or another possibility is that there's some other process, right? Something else that's cooling the plasma down. But really quickly, I mean, we still don't have all the answers, you know? And that's what makes this research so exciting, right? It's all these new questions.
It's like a reminder that science is always changing. We're always learning new things, right? Now,
Mhm.
this paper, it goes into another observation too, right? From March 17th, 2022, that's when the solar orbiter was even closer to the sun.
That's right. And with those closer observations, they were able to see something, well, really remarkable. They could actually see individual blobs inside the brightening.
Blobs, what kind of blobs?
Well, these blobs, they could be something that scientists have been thinking about for a long time. They call them plasmoids.
Wait, plasmoids. Aren't those like those little packets of plasma, the ones that they're supposed to be like a key part of magnetic reconnection?
You got it, like tiny bubbles,
Oh,
bubbles of magnetic energy. And they're just zipping around super fast.
yeah.
And seeing them, well, it just adds to the idea that magnetic reconnection, it's really driving these events.
So it's like we're finding the fingerprints at a crime scene for magnetic reconnection, I mean.
Exactly. And it's not just solar orbiter giving us these amazing clues.
Mhm.
The researchers, they also use data from another spacecraft, NASA's IRIS spacecraft. It's specifically designed to look at, well, the sun's transition region.
Now remind, what's the transition region again?
Oh, it's this thin layer, basically, sandwiched between the sun's surface, which is called the photosphere, and its atmosphere,
Ah.
the corona,
Okay.
and the transition region. It's wild, man. The temperature, it just like skyrockets. It goes from like a few thousand degrees to millions of degrees,
Mm.
but in a really short distance.
Whoa, so the transition region is like the ultimate hot spot.
You could say that. So what did Iris tell us? Well, the brightening. It was visible in the transition region too. That suggests that cool plasma, it was being ejected outward from the event.
Okay, so let me make sure I'm following this. We've got these bright streaks. They're flowing in two directions, right? Probably powered by magnetic reconnection, but the plasma, it's not as hot as we thought it would be.
Yeah.
And then we have cool plasma shooting out from the transition region.
You got it. It's a lot to take in.
But that's what's so cool about this, right? The sun, it's more complex than we thought, more nuanced.
All right, so what's the big takeaway here? What are we learning about the sun?
I think these observations, they really do provide strong evidence that these brightenings, the small ones, in AFSs, they're caused by magnetic reconnection. But what's really interesting is that while these events, maybe they play a much bigger role in how the sun works than we thought.
Okay, I'm with you, but how do these like tiny brightenings, how do they affect the whole sun? Okay, so imagine this. The sun, right? It's constantly making magnetic energy deep down in its core. And that energy, well, it needs a way to get out. These brightenings, they can be acting like release valves, you know,
Yeah.
letting that energy out.
So they're like pressure vents on a giant cosmic pressure cooker.
That's a good one. And remember, all this, it's happening within these arch filament systems, which are also, changing and moving around all the time.
It's like this giant web of activity driven by all this magnetic stuff. But why should we, down here on Earth, why should we care about these like tiny events? I mean, they're millions of miles away.
That's a great question. It's easy to think of the sun as like this distant thing,
Yeah.
you know, like it's not really affecting us. But the truth is, the sun is very active.
Yeah.
And that activity, well, can impact us here on Earth.
You're talking about space weather, right? Like
Yeah.
solar flares and those coronal mass ejections.
Exactly. And those things, they can mess with our satellites, knock out power grids, even be dangerous for astronauts. So the more we understand about the sun, about stuff like these brightenings, well, the better we can, predict space weather and maybe even prevent some of the bad stuff.
So it's not just about like science for the sake of science. It's about, keeping our technology working and keeping people safe.
Exactly. Oh, and here's another cool thing about this research. The researchers, they think that these brightenings, since they happen all over the sun, right? Maybe they're actually contributing to the heating of the
Yeah,
corona.
the corona, that's the outermost layer of the sun's atmosphere, right?
Oh.
And it's like millions of degrees hotter than the sun's surface. Scientists have been trying to figure that out forever.
Right. It's like you'd think the further you get from the sun, the cooler it would be. But that's not how it works with the corona.
So are they saying that these tiny brightenings, are they pumping enough energy into the corona to heat it up that much?
Millions of degrees. It's a big idea. Yeah. But it makes sense. If these brightenings are as common as we think, and if they're releasing enough energy, well, then yeah, collectively, they could be having a huge impact on the corona's temperature.
It's like the more the merrier. But for heating up the corona, I mean.
Exactly. Of course, we need more research to really confirm this idea, but it could be a big change in how we understand the sun. Like maybe we're finally close to solving this corona heating mystery.
Wow. Okay, so the story isn't over yet. What else did the researchers find?
Well, think about it. It's only now, really just now, that we're able to see these tiny little details on the sun. It's because of these amazing instruments we have now, like on Solar Orbiter. It's like we were looking through blurry glasses before, and now we can finally see clearly.
So are you saying there could be brightenings happening all the time, like all over the sun, and
Right.
we just never knew?
Yeah, it's definitely possible. And you know what? That brings up another question, another really interesting question that the researchers are asking.
Okay, let me guess. It has something to do with the corona.
You're on a roll today. The question is, could these brightenings, these small ones happening all the time, could they be the reason the corona is so hot?
Wow. So something so small could be responsible for, well, for heating up the whole corona.
That's the idea. It's a big idea for sure. And, if these brightenings are as common as we think they are, and if they're putting out enough energy, well, yeah, they could be adding a lot of heat to the corona.
It's like, how do I say this? It's like one tiny spark might not do much, but a whole bunch of sparks, well, that could start a fire.
Perfect analogy. But of course, we need more research. We need to look at more of these brightenings, in different places on the sun and at different times. And we need better models to really understand how all of this works.
So the mystery continues, but we're getting closer, right?
We are definitely. And what's so cool about this research is that, well, it shows how everything on the sun is connected. You know, these tiny brightenings, the arch filament systems, the magnetic reconnection, even the corona, it's all linked together.
It's like a giant puzzle, and we're finally starting to put the pieces together.
Exactly. And, it really makes you appreciate how amazing the sun is, right?
Mhm.
And how much more there is to learn. And thank goodness for missions like Solar Orbiter. They're really helping us push the boundaries of what we know.
Well, I think that about wraps up our deep dive for today. Big thanks to you for guiding us through all this. And to all of you listening out there, thanks for coming along for the ride.
My pleasure. And, next time you look up at the sun, just remember all those tiny little brightenings, they're hard at work shaping our star.
And until next time, keep exploring.